Hello student, I am Dr. S. L. Munde, Assistant Professor, Department of Mathematics, Sri RLT College of Science, Akola. Dear student, today's lecture we will see. In this today's lecture we will see theorem on counting of zeros. First we will see the theorem on counting of zeros. Then we will see corollary related to counting of zero. Then we will see some problems on counting of zeros topic. Okay. So what is the theorem? Let G be a region and F be an analytic function on a region G with zeros a1, a2, am repeated according to their multiplicity. Okay. If gamma is a closed curve in region G which does not pass through any of AK and gamma is equivalence to 0, gamma is homotopic here. Then we have to prove that 1 upon 2 pi I integral over gamma f dash of z upon f of z dz equal to summation k equal to 1 to m index of closed curve gamma at point ak. Okay, so this is the statement of the counting of zeros. Now let us we see the proof of this theorem. So what is given? So let us we have given G be a region and f of z be a analytic function on a region G which has a zeros a1, a2, am with a multiplicity 1. Okay. So therefore by using the definition of multiplicity 1 there exists a function g of z which is defined as on region G such that f of z equal to z minus a1, z minus a2, z minus am into g of z with g of ak is not equal to 0 where k equal to 1 to m equal equation number 1. So by using the definition of analytic function with multiplicity m, so we can define this another function. Okay. Now we will take the log on both sides of the equation number 1. Then equation number can be written as, or equation number will becomes log f of z equal to, here we will apply the formula log a into b, log z minus a1 plus log z minus a2 plus and so on. Last term will be log z minus am plus last term is log g of z. Okay. Now we will take the now we will differentiate with respect to z. Okay, now we will take the differentiation on both sides with respect to z. So what is the derivative of log f of z? That is 1 upon f of z into derivative of f of z, that is f dash of z, equal to derivative of log z minus a1, that is 1 upon z minus a1 into derivative of this term, that is 1, plus derivative of this term, that is log of z minus a2, that is derivative is 1 upon z minus a2 into derivative of this term, that is 1, plus and so on. This term will be derivative of z minus am log z minus am, that is 1 upon z minus am derivative of z minus am, that is 1, plus last term will be the derivative of log g of z, that is 1 upon g of z, and derivative of g of z, that is g dash of z. Okay, so we can write on this step. Okay, now we will multiply on both sides 1 upon 2 pi and integrate on both sides with respect to z along the curve gamma. Then we will get 1 upon 2 pi I integral over curve gamma f dash of z upon f of z dz equal to 1 upon 2 pi I integral over gamma 1 upon z minus a1 dz plus 1 upon 2 pi I integral over gamma 1 upon z minus a2 dz plus and so on, plus 1 upon 2 pi I integral over gamma 1 upon z minus am dz, and plus last term will be 1 upon 2 pi I integral over gamma g dash of z upon g of z into dz. Okay, Now by using the definition of the index of a closed curve, okay, so what is the term of this term? Okay, so left hand side is as it is 1 upon 2 pi I integral over curve gamma f dash of z upon f of z dz. Okay, so therefore by using the definition of index of closed curve at point a1, okay, so this can be written as index of closed curve, that is eta of gamma of at point a1, index of close along the curve gamma at a1 point, that is eta of gamma of a1, eta of gamma of a2 for this term, that is at a point a2, index of closed curve at a point a2, that is eta of gamma a2, and so on. This term will be eta of gamma am, and this term is can be written as 1 upon 2 pi integral over gamma g dash of z upon g of z dz as it is. Okay, now this term can be written in the summation form, or we can club in a one term, or this can be written as in the form of summation, that is summation k equal to 1 to m eta of gamma ak, where k lies between 1 to m, 1 upon 2 pi integral or gamma g dash of z upon g of z dz, equation number 2. Now here g of z is a analytic function on a region G. So therefore we can say that the ratio is also analytic function on region G. Therefore g dash of z upon g of z is also analytic on a G except for the those point where g of z is equal to 0. Okay. But actually g of z is not equal to 0 for the any point in region G, because the zeros of g of z will be 0 of f of z. Okay, so from equation number 1 we can say that. Okay, so therefore as f of z has only m zeros, we have given, since f of z has only m zeros, so therefore we can say that g of z has no zeros in region G. Okay, so which implies g dash of z upon g of z is analytic in the region G. So therefore by using the Cauchy's theorem, the integration or gamma g dash of z upon g of z dz equal to 0. Okay, now we will put this value in equation number 2 instead of this g dash of, that is 0. Okay, so this term will becomes 0, only term will be remaining 1 upon 2 pi integral or gamma f dash of z upon f of z dz equal to summation k equal to 1 to m eta of gamma of ak. Okay, and which is the required result of this theorem. Okay, hence the theorem is proved here. Okay, so this is the complete proof of the theorem. Now we will see the corollary of this theorem. So what is the corollary? The statement of the corollary is given as, let G be a region and f of z, or we can say that f is analytic on the region G. Gamma is any closed rectifiable curve in region G, and a1 to am are the only point in the region G which satisfies the equations f of z equal to alpha. Then we have to prove that 1 upon 2 pi I integral over gamma f dash of z upon f of z minus alpha dz equal to summation k equal to 1 to m index of closed curve gamma at a point ak, where alpha is any complex number. Okay, so this is the corollary. Now we will see the proof of this corollary. Okay, so what is given? So given that G be a region and f of z is analytic on region G, gamma is a closed rectifiable curve in region G, and also we have given a1, a2, am are the points in region G which satisfy the equation, that is f of z equal to alpha. Okay, so for k equal to 1 to m, so this can be written as at a point ak, f of ak equal to alpha for k equal to 1 to m. Okay, so this can be written as f of ak minus alpha equal to 0. We can write in this way. Okay, now to prove this theorem, let us we put g of z equal to f of z minus alpha for all z belongs to G. So differentiate with respect to z, so we get g dash of z equal to f dash of z, and derivative of this term will be 0 because alpha is a constant. Okay, but since we have given f of z is analytic on region G with zeros a1, a2, am, So therefore we can clearly say that g of z is also analytic on region G. If f of z is analytic on region G with these zeros, so from this equation we can say that g of z is also analytic on region G. If you take the integration of this term, so you will get g of z equal to f of z. Okay, if f of z is analytic, then we can say that g of z is also analytic on the region G with zeros a1, a2, am. Okay, so therefore by using the previous theorem, counting of zeros theorem, we can say that, or we can write 1 upon 2 pi I integral over cos gamma g dash of z upon g of z dz equal to summation k equal to 1 to m index of closed curve gamma at a point ak. Okay, so which is equal to 1 upon 2 pi I integral over curve gamma f dash of z. So put the value of g dash of z, that is f dash of z. Okay, and what is the value of uh, g of z? G of z we already considered. G of z means f of z minus alpha. So putting the values of g dash of z from this equation and g of z from this equation. So we can write f dash of z upon f of z minus alpha dz equal to summation k equal to 1 to m index of closed curve gamma at point ak. Okay, so this is the complete proof of the corollary of a counting of zeros theorem. Now we will see what is the actual the counting of zero. What is the definition of the counting of zero? Actual this definition we have to take before the theorem. Okay. So what is the definition of the counting of zero? If f g to c is analytic function with the zeros a1, a2, am, then the point z equal to a is said to be a zeros of f of z. If f of a equal to 0 with the multiplicity m greater than equal to 1, if there exists analytic function g to c such that f of z equal to z minus a to the power m g of z, where g of a is not equal to 0. Okay, so then this can be written as f of z equal to z minus a1, z minus a2, z minus am g of z, where g of z is not equal to 0 for any z in region G. Okay, so this definition is actually equal to the in counting of zeros. So this definition is also exactly equal to the analytic function with the multiplicity m. Okay, so this is the definition of the counting of zero. Now we will see the some problems on this theorem. Okay, previous theorem. So what is the problem? First problem, evaluate integral over curve gamma twice z upon z square minus 1, where gamma of t equal to 2 e raised to power it, where t lies between 0 to 2 pi. Okay, so this is the circle which represent a circle whose center is 0 and radius is 2. Okay, what is the solution? So what is given? Let us suppose that f of z equal to z square minus 1. Okay, so by using the definition of the uh, by using the corollary theorem. Okay, what is f of z? F of z is lower term and f dash of z means upper term. Okay, so if you compare this term to previous theorem term to this term, okay, if you compare this integral, so you will get f of z equal to z square minus 1 f dash of z equal to twice z. Okay, so at z equal to 1, so the factor of this term is z minus 1 z plus 1. So therefore z equal to 1 and z equal to minus 1 are zeros of f of z. बराबर है? So therefore by using the above theorems, 1 upon 2 pi integral over curve gamma f dash of z upon f of z dz equal to summation k equal to 1 to m index of closed curve gamma ak. Okay, so which is equal to put the values of f dash of z, that is twice z, f of z, that is z square minus 1 dz equal to what is the index of closed curve at a point a1, a1 that is 1 plus second is a2 that is minus 1. Okay, so therefore index of closed curve at a point minus 1 and at a point 1. Okay, so index of closed core at point -1 and at a point 1 equal to 1 because center is 0 and radius is 2. So therefore this point -1 and 1 will lies inside the circle. So therefore the value of this term will be the 1. Okay, so therefore it equal to 2. So transfer this term to RHS side, integral over gamma twice z upon z square minus 1 dz equal to 2 into 2 pi, that is 4 pi I. Okay, so this is the solution of this problem or integral, the value of the given integral. Now we will see the second problem of this. Evaluate integral over gamma z minus 2 upon z square minus 4z plus 3 dz, where gamma of t equal to 2 e raised to power it, t lies between 0 to 2 pi. So here center is 0, radius is 2. Okay, so what is given? We have given f of z equal to z square minus 4z plus 2. If you compare this integral to zeros of counting of zeros theorem, so this is the value of f of z and this is the value of f dash of z. Okay, so what is f dash of z? That is twice z minus 4. So if you take 2 is common, so you will get 2 z minus 2. Okay, so this is the value of f of z. So here z equal to 3 and equal to 1. Okay, the factor of this term will be the z minus 3 and z minus 1. Okay, so therefore as z equal to 3 and z equal to 1 are the zeros of the f of z. Okay, so therefore by using the theorem of counting of zeros theorem, we can write 1 upon 2 pi integral over gamma f dash of z upon f of z dz equal to summation k equal to 1 to m index of closed core gamma at a point ak. Ak means a1 and a2. Okay, so put the value of the f dash of z. What is the f dash of z? That is 2 times z minus 2. 2 times z minus 2 divided by 1 upon 2 pi integral divided by z square minus 4z plus 3 dz. So index of closed core at a point 1 and index of closed core at a point 3. Okay, so index of closed core at a point 1 will be the 1 because this 1 point will lie inside the circle because radius is 2, and this a equal to 3, this point will lie outside of the circle because radius is 2. So this point will be lies outside of the circle. So therefore index of closed core at a port gamma at a point 3 will be the 0. So therefore index of this term is 1 and index of curve of this term is 0. So therefore here 2 2 will get cancelled. Only remaining term is z minus 2 upon z square minus 4z plus 3 dz equal to pi. So transfer this term to RHS equal to pi. So this is the second example on counting of zeros theorem. Okay, so I will give you one example for homework. You have to solve this problem. Integral over gamma 3z square minus 4z minus 1 upon z cube minus 2z square minus z plus 2 dz. Answer is given as 4 pi I. Here gamma is mod z equal to 3 by 2. 3 by 2 means that is 1.5. So which represent a circle whose center is 0 and radius is 1.5. Okay. So these are the some problems on counting of zeros theorem. Okay. So in next lecture we will see another theorem.